So let us get started. Ria, could you please turn on the recording, please? Yeah, thank you. I hope that I am audible loud and clear to all of you, and my screen is visible.
Yes, sir.
Okay, very good. Today we have a number of things that are planned. So we will continue with our discussion about the Ethernet protocol. And last class, if you recall, I talked about this Ethernet protocol. I talked about the 802 IEEE 802 project, right, and how the Ethernet basically evolved, right. So we also saw that Ethernet is required because so you need so the main thing is basically when you are talking about the scale, that means that when you are talking about large number of computers, so between multiple different organizations, etc., etc. So basically you need the help of the network layer services, right. Now this network layer basically also needs support of the data link layer and the physical layer, right. And these two things are basically within the scope of the local area network as well as the wide area network. So you need some support to be provided by some protocol, by some standard for the data link layer as well as the physical layer. Now, when we are talking about the wired network, Ethernet has been kind of the very popular protocol that has consistently been in use. It started with the standard Ethernet, 10 Mbps Ethernet. Then it went to the 100 Mbps Ethernet, which is called the fast Ethernet. Then the gigabit Ethernet, which is 1 Gbps, and the 10 Gbps gigabit, 10 gigabit Ethernet, right? So this is how the Ethernet has evolved over the years. Actually, right now we are talking about 100 gigabit Ethernet and 40 gigabit Ethernet and so on. So the main thing is that we started with the basic internet, which is called basic Ethernet, which is called the standard Ethernet. And the standard Ethernet, if you understand, the rest of the things are easy because it's all about how you can manipulate few things in the standard Ethernet in order to have improved data rates, right? So it's all about data rates, right? And so let us try to understand this standard Ethernet. Now for the standard Ethernet, so this Ethernet basically gives you support in the data link layer as well as the physical layer, right? Now this data link layer, data link layer basically, so here actually we are talking about between two different data link layers in two different peers. We are talking about exchange of frames, right? That we know very well. Now, so these two peer data link layers, how they are going to talk to each other? They are going to exchange basically the address. I mean, through the addressing mechanism, basically through the addressing mechanism. It's going to identify. So what sort of addressing mechanism? I already told you, like in the different layers, the different types of addressing mechanisms that are in place. So you need some physical addressing mechanism, right? So what happens is that many times, when you buy your laptop or your computer, right? So desktop computer. So you go to the, you look through the specifications. In the specification, you must have seen that many times, I mean, most of the cases, basically, there is something called the network card, right? So this network card is nothing but, in technical terms, it is called the network interface card, NIC, right? So, when you are talking about the address, the physical address, basically, we are talking about the address of this network interface card. This network interface card is basically the one which helps the station, that means the computer or two computers, to have communication in the link layer, right? So basically this link layer addressing is provided with the help of this particular addressing mechanism. And last class we have already seen it, and we have seen, like, so this this physical address or the MAC address basically. No, so it's MAC address. So this MAC address, Ethernet MAC address basically, in the context of Ethernet, the Ethernet MAC address, it's basically 6 bytes, right? It's 6 bytes, and each of the bytes is basically represented using hexadecimal notation and are separated using colons, right? So you have 1 byte followed by a colon, second byte followed by a colon, third byte, and so on, all the 6 bytes. So 6 bytes means 48 bits. And the standard notation that is used is hexadecimal notation. So although I said bytes, etc., but basically the hexadecimal notation is used. So 1 byte corresponding to it, it's going to have its corresponding hexadecimal notation followed by a colon, followed by the next one, and so on and so forth, right? And so this is basically the way. So, and also I probably told you in the last class also that although the binary representation of these hexadecimals, so let us say that you are talking about a hexadecimal like let us say 4a colon 30 colon 10 colon 21 etc etc. So basically so the corresponding binary representation, hexadecimal to binary representation of 4a, right, is going to be there, right? And then you have the next hexadecimal number corresponding to it, the binary number will be there, and so on. So this is how it is represented. But when it comes to the transmission of the corresponding bits, right, the transmission basically starts from the least significant bit and not the way you write, not the most significant bit first. Okay? So when it comes to the transmission, basically the least significant bit is written first. Now it is this least significant bit, okay, which basically determines whether it is the multicast address or it is a unicast address. Right? So it is this least significant. So if it is unicast address, it is represented using the 0 bit, whereas if it is a multicast address, right, so it is 1 bit, right? So this is something basically what we covered in the last class. Now another thing which we did not cover in detail but is important and is not there in the slide but is there in the book is about the efficiency of the standard Ethernet, right? And this is important. So efficiency basically for the Ethernet is the ratio of the time that is used by the station to send the data to, we're talking about the ratio, right? So basically the time that is used by the station divided by the time the medium is occupied by the station. That's the efficiency. And so for the standard Ethernet, basically it is the efficiency, empirically has been determined to be 1 over 1 plus 6.4 times a parameter A, which is basically the number of frames that can fit in the medium, right? So this is basically this parameter, right? So you can also calculate the value of A, and this is something that we have done in the past, before your previous test also, so you can apply the similar kind of strategy. So so A can be calculated as propagation delay by the transmission delay, etc. So all these things, so all of these things basically you can utilize in order to compute the efficiency of the standard Ethernet. So I'm not going to go too much deep into this efficiency formula, etc. But remember that it is there, and in case you get any question in your next test or later on, you should know, like how to compute this efficiency. Now let us go further and let us try to understand the categories of the standard Ethernet. So basically the standard Ethernet basically has different implementations, right? So some of these different categories of common implementation or the different types of implementation of the standard Ethernet are shown over here. We are talking about 10 base 5, 10 base 2, 10 base T, 10 base F, right? So what is this 10 base X, right? 10 base X. We see that everywhere we have 10 base X. So somewhere it is 5, somewhere it is 2, somewhere it is T, and somewhere it is F. right? So 10 over here basically refers to standard Ethernet, and standard Ethernet gives you the data rate of 10 Mbps. 10 Mbps. So this 10 basically refers to 10 Mbps, which is the data rate of the standard Ethernet. Okay. Now this base, what is this base? Base is basically referring to the baseband signal, right? And you have studied before what is this baseband signaling. So baseband, right? So baseband signal. So this is this base that is referred to. Then there is a 5, right? Or you have a 2 or a T or a F, right? So basically this 5 or this X, the placeholder X, basically gives you the maximum size of the cable. Okay, maximum size of the cable in 100 meters. So 10 base 5. So 5 over here basically refers to 500 meters. Okay, so every 100 meter you get 1 point, right? So 5 means 500 meters. 10 base 2 on the other hand, not other hand, basically, only in this case it is like this, that 2 over here is basically 185 meters. It is close to 200. So this one. Now, then you have the T. T basically refers to the twisted pair cable, unshielded twisted, UTP, right? Unshielded twisted pair. And F basically refers to fiber optic cable. Okay. So this is basically the type of cable that will be used to implement. Now you have 10 base 5, so the topology that is commonly used is bus topology, and the thick coaxial cables are used. 10 base 2 implementations basically bus topology again with thin coaxial. Thick coaxial, thin coaxial are basically the diameters are different, right? And when we talked about these transmission cables, at that time we talked about the different types of thin and thick coaxial cables, etc. And 10 base T star topology is typical, and UTP. So this is basically this T is referring to this unshielded twisted pair. And this F over here, same star topology like before, but F over here refers to the fiber cable, right? Okay, so this is basically how you represent the different implementations of the standard Ethernet. Now let us talk about the encoding and the decoding scheme, right? So basically, so we are talking about what? We are talking about physical layer. So physical layer, basically the data signaling in the baseband is basically 10 Mbps, right? Baseband data signaling is done at 10 Mbps. Now, so basically, what happens is you have a sender, you have a receiver, and these two are connected by some wiring mechanism, for example, twisted pair or fiber, right? So at the sender end, basically this data that comes in is converted to the digital signal using Manchester encoding. Okay, so Manchester encoding mechanism is used, right? And then after that, that encoded signal is passed, and the receiver basically receives the encoded signal. It knows that it is Manchester encoding that is used, so it will use its decoder. Manchester decoder is going to be used in order to decode the data, and this data is going to be received, right? So this is how basically this encoding and decoding mechanisms are basically used. Okay. So as you know, like, when we covered, this Manchester encoding, in fact, at that time we have seen that Manchester encoding is good because it is, self-synchronous, right? So that is why basically in these implementations of the standard Ethernet, this, Manchester encoding is used. Okay. Now, so Manchester encoding or the differential Manchester. So what happens if you just recall? You have the mid-bit transition, right? You have the mid-bit transition, and that basically helps you in the self-synchronicity, right? So that is why it is very popular. Okay. Now, so let us take up one by one, each of these different Ethernet implementations. The first one is called the thick Ethernet, or the 10 base 5 Ethernet, right? So it's thick Ethernet or the 10 base 5 Ethernet. So here basically, so here the term thick Ethernet basically refers to the fact that the cable that is used is thick. So this is how it looks like. So as I told you, like 10^5 basically uses the bus topology, right? So this is your bus topology that you can see in this particular figure in front of you. So you have this transceiver cables basically which fall onto the onto the coaxial cable, the thick coaxial cable, and these thick coaxial cables are basically quite thick, right? And they are not very you cannot bend them very easily, so they are not very flexible type, right? So this is why they are very popular to be used as bus cables basically, right? So with the help of these transceivers, basically, each of these different stations, they connect to the main thick coaxial cable, right? The maximum length of this thick coaxial cable is 500 meter, whereas the transceiver cable basically runs up to a maximum length of 50 meter. Now, this transmission from the station basically is done through this transceiver cable, okay, and through this transceiver, which basically is connected through the tap to the main thick coaxial cable, and this transceiver basically, this transceiver is basically responsible for the transmission, the reception, and the detection of the collisions, right? So this transmission basically helps in the transmission, reception, and the detection of collisions, right? And so basically, this transceiver basically is connected to the station via this transceiver cable and provides the separate paths for SENHA. So this is very important, right? So for transmission and reception, basically, in 10^5 implementation of the standard Ethernet, so there are two directions, right? So the sending and the receiving, for which you have separate paths, you have separate cables, you have separate basically paths basically provided through physical cabling, and for one for sending, the other for receiving, right? So obviously, if you are separating them, if you are sending, if you are separating the sending and the receiving physically, then so where can the collision happen? The collision, only place that the collision can happen is over here. That means the thick coaxial cable. Only over here this collision can happen, right? So you have to take care of the collision using MAC layer protocols, right? So let's not worry about that part. But what I wanted to highlight over here is basically the use of the two types of cables, and one basically ensures inherently, it ensures that there is no kind of collision that is going to happen, and the rest of the collision is basically done by the thick coaxial cable. It is handled by the thick coaxial cable because that is where the collision is going to be handled, right? Collision will be occurring, and it has to be handled using appropriate protocols in the higher layers. Okay, so that's the thick Ethernet, right? And then basically this thick Ethernet has its own limitation, because as I told you, like it is not very much bendable, etc. So that is why basically this thin Ethernet, which is basically this 10^2 variant, so it is used, right? Again, same thing, bus topology like before. So you see that you have the cable running between the two ends, and you have this thin coaxial cable, and you have these transceiver units which are going to do the same thing like before. But there is a difference, right? So this transceiver, because the cable, the main cable, basically it can bend, right? So it can pass very close to the stations because it is bendable, right? It can pass very close to the stations, right? So the transceiver basically over here is part of the network interface card, and it is installed inside the station. Okay, so here basically, if you have this kind of thin coaxial cable, the collision will occur in the thin coaxial cable, right? And it is more efficient than the 10^5 implementation, because the thin coaxial cables are thin, so physically they are thin, so they are less expensive than the thick coaxial cables. And same thing, basically this is also cheaper, like these these transceiver P connections basically are also much cheaper than the taps that are used, right? So that is why basically these 10^2 implementations became more popular, right? But remember one thing, that unlike in the case of this 10 base 5, where we talked about 500-meter cable, here actually we are talking about close to 200 meters, not exactly 200 meters, which is 185 meter, right? And remember that how much is the length, whether it is 500 meters or 185 meters, how do we determine, how much the length is going to be? Basically, this is determined through different studies where basically technologists or scientists, where they have measured how much is the attenuation through each of these different cables. So basically, it is observed that in a thick coaxial cable, it is sufficient to have this 500-meter this thing, and over here, 185-meter, right? So otherwise, if you increase too much, then the attenuation levels are going to be high. Okay, so next comes the 10 base T, the twisted pair Ethernet. So here it is slightly different. Over here it is slightly different. So the same cable, sorry, not the same cable, the same approach, basically, so the same thing, the 10 base something, but the cable over here is the twisted pair. Now this twisted pair, so if you recall, so we talked about twisted pair cables before, several lectures back. We talked about the twisted pair. So what is the beauty of the twisted pair cable? Who can tell? Why twisted? Why twisted in a twisted pair cable? Who can tell? Why the twisting is done in a twisted pair cable? I hope that all of you are listening to me. So I'm asking something, so from a topic which was before your previous test. Why the twisting is done? Who can tell? Twisting in the twisted pair cable? No one. That's strange. So basically, this twisting is done in order to cancel out exterior electromagnetic interference, right? So this twisting is done in such a way that this electromagnetic interference is going to be um, cancelled out, right? So anyways, so these twisted pair cables are going to be, you see, you have to listen to me, right? In the class, I'm telling you, if you are listening to me, it is good. But in case you are not listening, so in your tests, basically, that will get reflected, right? So it is very important. Once again, I appeal to all of you that you listen to me, because it's online, virtual. I cannot see what you are doing, whether you are browsing Facebook or Twitter or whatever you are doing. I do not know. But in your own interest, please make sure that you listen in the class. And half of your preparation basically gets done if you listen carefully in the class. Not only this class, any class basically. Right. So anyways, so let me continue in the interest of time, but make sure that you be responsible for yourself and listen. Anyways, so let us continue. So this here, over here, we are talking about twisted pair cable. So that is why you have this T written over here. Okay, so now this twisted pair over here is connected in the form of a star topology, right? So basically, so you have these different stations, right? Multiple stations, and you have a hub, right? You have a hub. So this 10 base T connection basically provides you to have this kind of a star kind of formation, right? At the hub, a star kind of formation at the hub, through which you have different connectors. Okay, so these UTP cables, basically these UTP connector cables, which connect to the different stations, right? So this is the star topology. So physical layer, basically the star topology is used in 10 base T. Okay, so here basically the stations are connected to the hub using two pairs of twisted pair, right? So using two pairs of twisted pair. So you see that so if there is so before I do this, so let me ask you. I told you that two pairs of UTP cables will be required. Two pairs of twisted pairs are going to be required. Why two pairs? Who can tell? Why two pairs? Can somebody confirm that you all are with me, or just to make sure that online I'm not disconnected? Anybody? One of you please confirm that you are able to hear me.
Yes, sir, you are audible.
Yeah, I am audible. Okay, very good. So let me continue. So why two pairs? Basically, one for same like before, one for sending, one for receiving, right? So two pairs of twisted pairs are used, right? So between what? Between the computer and the hub, right? So now this hub basically, as you can see over here, and as I told you, forms the star topology, right? Can help the stations to be connected to it using the star topology, right? So this so you see this star topology basically can help um, this hub basically to replace the coaxial cables, and as a result basically any kind of this thing collision that is going to happen at the hub itself, right? So any kind of collision that is going to happen will be happening at the hub, right? So it is here, not here or here or here, the collision is going to happen. Here it is going to happen at the hub. So this is basically the way this twisted pair Ethernet works, right? And an analogous this thing implementation for the standard Ethernet using fiber cables, right? So 10 base F. So here basically this fiber Ethernet is used, which uses again the same topology like before, like the T connection. Over here we have the fiber connection. So basically, so here we have the fiber connection 10 base F, the same star topology, and the only difference is over here it is not twisted pair but fiber optic cables which connect the different stations, right? So uh, that's all. So here is the summary of all of what I just mentioned. So as you can see over here, the maximum length values are also given over here. And as we know that fiber channels are basically more, what should I say, like, more efficient, right? So the performance, like, so in terms of the attenuation, etc., are much less. So that is why, so these fibers basically give you much more, much more efficient communication mechanisms, or the length of the cable can also be much more, okay, in fiber. So this is basically the summary of these characteristics. So you have to go through. So these things are basically there in your textbook, which is the Foruzen book, right? So all of you, please make sure that you go through the textbook as well. Now let us talk about the scalability, right? Because scalability is very important, and it is the scalability issues because of which basically this performance of these computer networks degrade. So let us talk about, if you are talking about like a couple of computers, one, two, three, four computers, 5, 10 computers, it is fine, right? You can all put them into the same bus and it all works, right? So if you are talking about a bus topology, you can just have, you can increase. So if you have a long cable, right? So you just, have these transceiver cables, drop into the main coaxial cable. So that is fine. But so the problem with this kind of connection basically is that scalability cannot be achieved uh, much, right? So for this basically you use a device which is called the bridge, right? You use a device which is called the bridge. The purpose of the bridge is basically to divide the network into multiple parts. So over here in this example, the bridge is a device which divides this network into two parts. So what sort of division we are talking about over here? We are talking about division bandwidth wise. That means so bandwidth is going to be divided across the bridge, right? And also you are dividing the collision space. You are dividing the collision space. So now you see that if you take care of these two issues, basically this so the efficiency of communication basically is going to improve, right? So so bridges basically can help in improving the effective bandwidth of communication by raising by splitting the bandwidth space as well as the collision domains, basically, right? So so that's the bridge, right? So so without bridging, you have all the stations sharing the same bandwidth and collisions can happen. So you see that over here the chances of collision are much more compared to over here, because over here only these stations are going to share the bandwidth and only these stations are going to share the bandwidth, right? And the collision also, the chances of collision also are reduced compared to the scenario over here, right? So this is very important. Yeah, so we have already talked about it, so I'm going to skip it now. So over here you see that in this example, right, what the bridge has done. So it has reduced the collision domain into three, right, groups of three. So you have four domains, collision domains. So every domain has only three computers, so basically connected to it. So the chances of collision are going to be reduced. On the other hand, if you had all of these connected like this, the chances of collision would have been much more. Pretty straightforward, not much difficult to understand. But bridge basically is helpful, but you can extend this particular idea, okay, to connect different domains through a device called the switch. So what the switch does is exactly like what I said for the bridge, but much more. It's going to split into several domains, right? It's going to split the space, the collision space and the bandwidth space into several domains. Okay, so basically, so this is basically, so the switch basically it's a layer 2. It's a layer 2 device, and in the switch basically you have several ports. So you can have n number of ports. Okay, but the way this switch has been fabricated is that any kind of connection across is going to be taken care of through the sophisticated mechanism that is in place inside the switch. Okay. Now, okay. So you see that the formation of this switch, the concept of this switch, right? This has been very popular because that gives you a lot of flexibility in terms of scaling up the connectivity. Now let us talk about the switched Ethernet. Okay. Now you see that this is a switch, and each of these different computers are connected in this manner, right? So there is a separate transmit and receive cable basically running between them. So this is basically this full duplex mode communication. And so here basically it increases the capacity of the domain from 10 Mbps to 20 Mbps as per the example that we had seen before. So instead of using one link between the station and the switch, the configuration basically this uses two links, one to transmit like this and one to receive, right? So you can have a full duplex switched Ethernet in this particular fashion. So if you do have a full duplex switched Ethernet implementation, then obviously you do not really need to go for the CSMA CD kind of protocol that you had learned before for medium access control over the wired Ethernet implementation. So basically in a full duplex switched Ethernet, each of the stations is connected to the switch via these two different links that I said, and each station or switch can send and receive independently without worrying about the collision, right? So this is basically the switched Ethernet implementation looks like. Now this switched, any questions so far? Any question? Okay, let's proceed. So switched Ethernet became very popular because that helped in the growth of the Ethernet implementation. Now, what about the speed? Because when Ethernet was becoming popular, at that time there were two other competing LAN protocols which were becoming much more popular. These are called FDDI and the fiber channel, right? Because around the year 1990, basically, you know, so these devices, when they started becoming becoming popular at that time, fiber channel, FDDI, etc. Actually, this is when basically, I was also a student during those times, and I remember the growth of these fiber channels, FDDI protocol, etc., etc. Right now, so Ethernet basically was quite flexible. It could handle number of different scenarios and so on. It was quite popular, and this Ethernet community wanted to promote Ethernet by making the speed quite competing with this FDDI fiber channel and other similar competing technologies. So basically, there was a task group which worked on it, and it came up with the 100 Mbps Ethernet. So 100 Mbps Ethernet means that the transmission speed is 100 Mbps. And in short, and in the community, this 100 Mbps Ethernet is called the fast Ethernet, unlike the 10 Mbps counterpart, the standard Ethernet counterpart. So you see, there was a huge jump from the 10 Mbps to the 100 Mbps. So that was basically how this 100 Mbps came into being, right? So these are the goals of this 100 Mbps Ethernet. So first is to upgrade the data rate, which was the primary, the most important, the fundamental requirement, right, behind this initiative. The other equally important component was the compatibility with the existing implementations of the Ethernet, because you did not want to scrap out the existing Ethernet implementations that were in place in the different organizations or at homes. So you simply wanted to use this existing Ethernet and make a fast data rate variant, the 100 Mbps variant, while ensuring that the existing implementations were compatible to the new one. Okay, so it basically kept the same kind of 48-bit addressing mechanism, right? And also it kept the same frame format, right? And also it kept the same the minimum and maximum lengths of the frame. So let us now talk about the topology, right? So the fast Ethernet basically can connect two stations together, or it can also help to connect more than two stations. So this is the case of the two stations connected point to point, and this is the other one, which is multiple stations, more than two, connected to the help of the switch. So everything same like before, but what has changed is now that you need higher data rates, right? So so this is basically the same kind of switched Ethernet with 3 or more stations, etc., and star topology. So it is this way basically. This this thing, the configuration is done. Right now. So we'll talk about this physical implementation of this fast Ethernet. But another thing that is important to understand is this fast Ethernet basically added over the standard Ethernet. It added a new feature which is called the auto negotiation feature. So this name suggests what this auto negotiation is. As this name suggests, basically this auto negotiation allows a station or a hub a range of capabilities, right? So there are different types of capabilities that this auto negotiation allows. So what is this main thing over here? What is this main capability that is implemented? Basically, two devices over here through auto negotiation can automatically negotiate the rate of operation. So in other words, if there is one device which offers you the data rate of 100 Mbps, and there is another one which offers you the data rate of 10 Mbps through this auto negotiation mechanism, these two devices, they can basically connect with each other. They can communicate with each other, right? So so basically this compatibility, basically this auto negotiation helps you to incorporate the compatibility, right? So to allow the incompatible devices to connect with each other. 100 Mbps capacity with 10 Mbps capacity, how you can make them talk to each other. So this is basically this auto negotiation. Okay, so I didn't have a slide for it, but I just wanted to mention about it briefly because this is different from the standard Ethernet, right? So here in the fast Ethernet, you have this feature of auto negotiation. So coming back, let us look at physically what is there in the fast Ethernet. So there are broadly three implementations of this fast Ethernet. The first one is called the 100 base TX. The second one is called the 100 base FX. And the third one is called 100 base T4. Right? Okay. So here you see that this one uses the Cat5 UTP. Cat5 UTP, right? 100 base TX basically uses Cat5 UTP. 100 base FX basically uses the fiber, only 2 wires of fiber, and T4 basically represents the 4 wires that are used, right, in this implementation. 4 category 3 UTP wires, right? So this is basically what is used in the 3 different implementations, the physical implementations of the fast Ethernet. Now, then what is done? You need to take care of each of these using the corresponding encoding mechanisms, right? Again, over here, Manchester encoding is used, right? So Manchester encoding. So, but Manchester encoding, it's only if you are using Manchester encoding, that's not going to be sufficient. So what is done? You see that this 100 base TX. Okay, so the first one, this is your 100 base TX. So it uses a combination of MLT3 encoding with 4B5B encoding, right? So now this 4B5B, but MLT3 actually it was out of syllabus, so I didn't cover this. But basically, so just for you to remember that this is another type of encoding mechanisms, MLT3 encoding, which is used in the fast Ethernet. But this 4B5B basically can help you with the synchronization, and this so this basically offers you quite good bandwidth, basically bandwidth performance, and it can help you in the communication. Now this FX over here, 100 base FX, is more or less the same like before, but over here, instead of using MLT3 encoding, energy I encoding is used, right? So energy I or energy I, whatever way you call. So energy I encoding is used, right, over here. And 100 base T4 basically uses only the 8B60 encoding, only the 8B60. So all of these like 4B5B or 8B60, etc. So all of these things basically or energy I, etc. The only thing that you do not know is MLT3 encoding, but for you just to know that this is yet another type of encoding mechanism which you have not learned in this course, but it is sufficient to know that MLT3 is used in the fast Ethernet for encoding. In which configuration? In the 100 base TX configuration only. So here is the summary of the comparison between each of these. So then came the gigabit Ethernet. Right? So gigabit Ethernet was even more ambitious. So in gigabit Ethernet, the whole idea was to improve the data rate, okay, even further, right? So how much data rate? 1 gigabit. 1 gigabit, that means 1000 Mbps, right? So earlier it was 100 Mbps, and now you have increased it to so 10 Mbps, 100 Mbps, and now we are talking about 1000 Mbps, right? That was the goal. So everything very similar to what we have seen for the standard and the fast ones. Okay, so backward compatibility was important, right? Existing implementations of the standard or the fast Ethernet, you need to have the gigabit Ethernet also to be compliant with it. And it was required to improve the data rate to 1 Gbps or 1000 Mbps. So, and another thing, that auto negotiation feature that I told you for the fast Ethernet, that was also preserved in the gigabit. Right now, this gigabit Ethernet basically operates in different approaches. Right, one is the two different modes, basically two different modes. Right, so one is the full duplex mode, the other one is the half duplex mode. So in the full duplex mode, obviously there is no collision, right? So how much the cable length is going to be, that's determined solely because of the signal attenuation, right? So you study the signal attenuation and you determine how much the length of the cable is going to be, and you do not worry about the collision, right? In half duplex, basically, a switch is replaced by a hub, right? So which basically acts as the common cable in which a collision may occur. Right, so in half duplex, basically, not only you need to think about the signal attenuation, but also you need to take care of the collision that can happen at the hub. So in order to handle this collision, basically you use CSMA-CD kind of approach. Over here, actually in full duplex mode, you do not need it. So these are the different types of gigabit Ethernet topologies. I'm not going to go through them. This is quite obvious. So all these point-to-point, star, two-star, hierarchy of stars, etc., using several different switches, connected in a tree-like kind of fashion. So all of these basically are the different types of topologies that can be implemented with gigabit Ethernet. Now, like the standard Ethernet, like the fast Ethernet, the gigabit Ethernet also came up with its own different implementation variants. 1000 base SX, 1000 base LX, 1000 base CX, and 1000 base T, right? So these are the different types of variants of it. So you see that the corresponding fiber types are also mentioned over here, on which this gigabit Ethernet can also be implemented. So like the fast Ethernet, etc., so here also you need a combination of different encoding mechanisms, like the ones over here that are shown, right? And yeah, so these are the ones basically, so another one, 4D PAMs, basically 4D PAMs also you do not know, but it is again another, it is just sufficient to know the names, right? So so 4D PAMs is used in gigabit Ethernet as an encoding mechanism, right? Then came the 10 Gbps. So 10 gigabit Ethernet, right? So 10 gigabit Ethernet, you wanted to make it even faster, use the same format, the 48-bit addressing format, keep the same frame format, keep the same minimum and maximum frame lengths. So only thing is that you want to upgrade the data speed, the data rate to 10 Gbps. Okay. So this was the 10 gigabit Ethernet implementation. Okay. Now, what is the difference between 802.3 and Ethernet? So if you recall that in the last class, we talked about the different 802 series of standards, right? So 802.3 is one such standard, right? So 802.3, what is the difference? 802.3, people often use them interchangeably, but you should know what is the difference between them. So 802.3, IEEE 802.3 is simply a standard, whereas when we are talking about Ethernet, Ethernet is an implementation which follows this particular standard. So Ethernet is a set of technologies and protocols that are used primarily in LANs, whereas IEEE 802.3 defines the physical layer and the medium access control sublayers of the link layer for wired Ethernet networks. Okay, so 802.3 IEEE is original standard that was given for the 10 base 5 implementation. Very quickly, we need to understand two more things, and then we'll be done for today. The first thing is, what is the difference between the switch and a hub? So I want you to go through these, but I would just like to mention the main differences. So here actually you are talking about in hub, you are talking about a physical layer device, right, which operates in the physical layer. Switch, on the other hand, is a data link layer device. Okay, so switch is basically a data link layer device, right? The other difference is basically that hub offers you half duplex transmission, whereas the switch offers you full duplex transmission, right? And there are a few other points of difference between them, which I'm not going to go through, but I would leave you and I would urge you to go through them yourselves. The last point that I'm going to mention is the spanning tree protocol. This is also something that is very important. It's not there in your book, but if you listen to me, it will be clearer. And you can also take help of standard materials that are available on this particular protocol in the internet, right? There are so many ebooks also that will talk about the spanning tree protocol. So what is the spanning tree protocol? Spanning tree protocol, as you know, right? So what is a spanning tree, right? So spanning tree, all of you know, right? Spanning trees basically help you to reduce or to get rid of the loops, right? So if you are talking about a graph, right? Or let us first talk about the network, right? So whenever we are talking about network, redundancy is something that is desirable. You need redundancy because you need multiple different interfaces through which the packets can flow through, right? Because if there is one interface which cannot be used for one reason or other, there are other different interfaces so that you do not have your communication blocked. Now, redundancy is good, but redundancy also brings you the problem of loops, right? So in the graph, if you think of the network to be a graph, so in the graph you can have cycles, right? So that is the reason basically the spanning tree protocol basically gives you a mechanism to have a loop-free logical topology from the physical topology that has the loops. Loop-free logical topology. So the working for it, I have mentioned over here. I would urge you. I'm not going to spoon feed each and everything, but I would urge you to understand yourselves. But the essence is what I told you just now. So there are different so ports that are used, right? So each of these ports that are used by the STP goes through different states, right? So each of these ports basically goes through different states. There is the blocking state, the listening state, the learning state, the forwarding state, and the disable state. So each of these states I would urge you to go through, but I would just like to highlight some of the important ones. The blocking state basically blocks the port which if you keep it open, basically is going to lead to the formation of the loops, right? Then you have the listening state. Listening state is basically the first state. Basically, the port is listening for any incoming packets, etc. It also provides the interface to the blocking state, right? And then you have the learning state. Learning state means like the first time, basically, if there is some packet that comes in, through this basically the interface it learns, so which frame basically goes through which particular port. So that's the learning state, and then you have the forwarding state. Basically, so it is basically this state helps in the forwarding of the different frames. And then you also have the disabled state, quite obvious. And so bridges are very important, right? So whenever we are talking about local area network, bridges are very important. So these local area networks can help you to form different, it can help you in the different implementation of internet or local, or the token ring with the help of these bridges. So what is a bridge? Basically, it's a device that decides whether a message from someone to someone else is going to go to the local area network in the same organization or same building or the same LAN, or to somebody else in a different LAN. So basically these bridges basically help in doing this, right? So bridges basically can examine each message on the LAN and then pass them to either a different LAN, or it is going to route to the same LAN depending on where the destination is, right? So this is basically how these bridges are used. This is a bridge and you have one LAN, right? LAN A, this is LAN B, and bridges basically help you to either confine the messages within the same LAN or to pass them on to the other LAN, right? So there are different types of bridges: root bridge and non-root bridge. Root bridge is basically the one that offers an interconnection point for all segments, right? So all the bridges in a LAN are going to have a path to this particular root bridge, whereas a non-root bridge is the one that is that doesn't have this kind of feature, right? So it's not a root. So today's Ethernet, as I was telling you before, is 10. It has evolved even further. It is 10 gigabit Ethernet or 100 gigabit Ethernet, depending on the implementation that is there in the organization that you are in, right? So that's about it. And thank you very much. So please make sure that you go through all of these. Tomorrow we have another very exciting topic, IP addressing, which is coming.